All right, so we are continuing our discussion of section 8.2, the section on series. So I'll just not rewrite, but I'll just, for video purposes, we're on series. And I want to do another example. Okay, so let's say you had a series like this. And I want to phrase it right. But usually it starts, yeah. Okay, what's the first term of the series, of this series? Where n equals 1 to infinity, and the term of the series is 1 over n. What would the first term of the series equal?
1.
1. That's right. What about the next term? That's right, Claire. That's right, OPM.
1/2 or 0.5.
Okay, good. Next term of the series. All right. I think we're getting a feel for this. That's right, Jonathan. That's right. OPME, I forget who. Yep. So do you see how the series just by the way, the terms of the series, what are the terms of this series approaching? They're approaching 0. That's right, Susanna. That's right, OPME. And what I want to know is, does the series converge? And incidentally, this is such an important series that we actually give it a name. So let me write the name here. This is what's called a harmonic. A harmonic series. Is a harmonic series a geometric series? No, that's right, Susanna. It's not, because look, if you take the second term and divide it by the first term, okay, you look at that ratio. That's 1/2 divided by 1, and that's 1/2. But if you take the third term and divide it by the second term, that's 1/3 divided by 1/2, which is 1/3 times 2 over 1, and that's 2/3. So you see, a 1/2 is not equal to 2/3. There's no common ratio here. There's no common ratio. So this is not a geometric series at all. But the harmonic series, the terms are approaching 0. So do you think the series will converge? Will there be a finite sum for this series? Okay, Jonathan thinks the series will have a sum. He thinks it will converge. I mean, the terms of the series are approaching zero. They're dying down. Okay, OPM thinks diverges. Well, in fact, that is correct. This series does diverge. The harmonic series diverges. And this is something that is really quite amazing to students when they first see this. I mean, here you are, you're adding these terms. The terms are getting smaller and smaller and smaller. How can it be that the harmonic series diverges? Well, the point is that one thing to think about is the terms of the series are getting smaller. They're approaching zero, but the rate at which those terms approach zero is not fast enough to cause the series to converge. It's a little bit like the improper integrals when you had one of the limits being infinity. Some of those series would converge, others would diverge, because it has to do with how the rate at which the function would, approach zero. It's the same kind of thing. Well, that's a good question, Jonathan. What does define fast enough to converge? A lot of times, what we'll do, that's a very good question. Certainly, if a series can be compared to, if you have a series and you can show that series is for equivalent as you move out into the series, as you move out, if the terms of that series become equivalent to a convergent geometric series, then I think we could say that series converges. That's one way to talk about fast enough to converge, because a convergent geometric series would be one where the common ratio is less than 1, or the absolute value of the common ratio is less than 1. That's what I mean. So, yeah, well, Jonathan, you're going to be spending a lot of time in Chapter 8 sort of getting an intuitive feel for what fast enough to converge means. Okay, but we're sort of just touching the surface here of this content, these series. I mean, there's a whole book written on these infinite series, and but generally, the general idea is that a series will converge if its sequence of partial sums approaches a limit, a finite limit. That's the general definition. If that were to happen, then the series is dying down fast enough to converge, so to speak. There's no great, that's sort of, well, I think, keep that thought in your mind, Jonathan. Keep that thought in your mind. Let's at least I think it's valuable for us to try to look at this why a proof of why this harmonic series diverges. Because if you ask the normal person, they're going to say that series converges, right? So in the book here, this is the proof, and this is very famous. I learned it when I took calculus. Show that the harmonic series is divergent. There's the harmonic series. And what we can do is we can look at some partial sums of the series. They say for this series, for this particular series, it's convenient to consider some partial sums, the second partial sum, fourth partial sum, eighth partial sum, 16th partial sum, 32nd partial sum. Look at those partial sums and show that they become large. Okay, so look at what you do here. So The second partial sum is just the sum of the first two terms. That's, 1 plus a half. The fourth partial sum is the sum of the first four terms. But the third and fourth term, a third and a fourth, can be that is greater than a fourth plus a fourth. So the fourth partial sum is greater than, well, and a fourth plus a fourth is a half. So the fourth partial sum is greater than 1 plus 2 over 2. The second partial sum is equal to 1 plus 1 over 2. The fourth partial sum is greater than 1 plus 2 over 2. Now the eighth partial sum here, it can be shown that that's greater than 1 plus 3 over 2. You see how they're grouping together fractions and coming up with this result. Let me go a little further here. The sixth partial, so the eighth partial sum is greater than 1 plus 3 over 2. The 16th partial sum, which is the S sub 16, it's the sum of the first 16 terms, that can be shown to be greater than 1 plus 4 over 2. Okay, so I mean, what you're seeing there is that, I mean, you're probably wondering, well, how's this going to help me? But I mean, what they're saying there, what you're seeing is true, right? What you're seeing is true there. Okay, so for the harmonic series, let me go to the whiteboard here, and you have this in your ebook. It's example 7. Let me just write it. Okay, so the fourth partial sum, let's start there, is greater than 1 plus 2 over 2. This is now for the harmonic series. This proof, by the way, that you're going to see, this proof in example 7, it was invented by the French scholar Nicole Oresme. He lived from 1323 to 1382. So this is like 800 years old, what you're seeing here. Okay, so the eighth partial sum, but this is what made this person famous, coming up with this proof. Eighth partial sum is greater than 1 plus 3 over 2. 16th partial sum is greater than 1 plus 4 over 2. Now, let's go to the 32nd partial sum. Okay, and by the way, notice that 4 is equal to 2 squared. Okay, and there's a 2 here. 8 is equal to 2 cubed. There's a 3 here. 16 is equal to 2 to the 4th. There's a 4 here. What would you guess that the 32nd partial sum is greater than? If you add the first 32 terms of the harmonic series, it would be greater than 1 plus something over 2. That's right, Jonathan, 5 over 2. Because 32 is 2 to the 5th. So there's a pattern here. There's a pattern. There's a pattern. And in general, well, let me do one more. What about the 64th partial sum? that would be greater than 1 over, I'm sorry, the 64th partial sum would be greater than 1 plus what number over 2? Well, what number is going to go here? That's right, OPM, because 64 is 2 to the 6th power. Okay, so in general, the partial sum, okay, and I want to kind of have it look good here. So I'm just looking at these certain partial sums, but it's okay. The 2 to the nth power partial sum is going to be greater than 1 plus what over 2? What's going to go here? Based on what you're seeing here on the left, the pattern of these partial sums. Good, Victoria, it's going to be an n. It's going to be an n. So this means then, as n goes to infinity, the partial sum, s sub 2, the 2 to the nth power partial sum, has to, well, let me put it like this. Let me put it this way. The limit as n approaches infinity of the 2 to the nth power partial sum, that would have to be greater than the limit as n approaches infinity of 1 plus n over 2. But what is the limit of 1 plus n over 2 as n goes to infinity? What's this equal here? Well, as n goes to infinity, 1 plus n over 2 would go to, what would it have to go to? That's right, Susanna, it'd have to go to infinity also, right? That's right. So this means that the sequence of partial sums, okay, that sequence of partial sums, okay, which we denote, I got to be a little bit careful here. Hold on here. It's this sequence of partial sums. That sequence of partial sums diverges. And it's not every partial sum that you're looking at. You're looking at basically a snapshot here of partial sums, but it's okay. If you, the fact that this subset of partial sums diverges means that the sequence of partial sums diverges. So therefore, this means then, therefore, the series diverges. And this really is quite an amazing result, because it's not something that would easily be discovered, you know, but it's the truth. The truth is the truth is the truth, and it is the truth. And it makes our lives a little more complicated, right? Because now with this result, we have a series where the terms, this harmonic series, where the terms of the series are getting smaller and smaller and smaller, approaching zero. Yet the series, when you add up those terms, the series equals infinity. The series diverges. So we can't just you know, we have to be careful with our intuition. And, you know, but at any rate, all right. So that being said, are there any questions before I look at a few more examples here with you? All right, if you're good with that, then let's go continue on here. Okay, let's take a look at this example. Okay, let me give you a moment to copy it down. All right, class, so let's take a look at this. So this is an interesting series. Could we write this series like this? Could we just write 1 as 1 to the nth power and leave the root 2 alone and it's raised to the nth power? Is that okay? I mean, 1 to the nth power is always equal to what? Right, 1 to the nth power always equals 1. Now, why would I want to do this? Why would I want to rewrite that like that? Well, if I do that, then I can write the series like that. And that's going to be helpful. That's going to be helpful. Do you know what kind of series this is? I mean, if we were to write out some terms of the series, if we were to write, that's right, Jonathan, it's a geometric series. Because if you take 1 over root 2 to the 0th power, that's right, plus 1 over root 2 to the 1st power. So what I'm doing is I'm writing out some terms of the series. Plus 1 over root 2 squared, okay? Plus 1 over root 2 cubed, and so forth. And if you do, right, it's just going to be 1 plus 1 over root 2 plus 1/2 plus 1 over 2 root 2. What's the common ratio? What's the common ratio for this problem? That's right, Jonathan, 1 over root 2. So it is a geometric series. And notice that the absolute value of R is less than 1. So it is possible to find the sum of the series. It absolutely is. Okay, are there any questions on that? Sometimes you have to get your hands dirty a little bit, right? To just, I like to explore, and sometimes exploring with a series means writing out some terms so that you can get an intuitive understanding of the series. Well, this is a convergent geometric series because common ratio is less than 1. So let me show you what we can do here. Let me go to the next page. Okay, so what I've done is, I wrote the series as I showed you. And this series, if we, like the index starts at n equals 0. But if we wanted to change the index to starting at n equals 1, then the nth power, if we adjust it to be the n minus first power, the two series, these two series are the same series. They're the same. And I show that on the right-hand side because on the right-hand side, what I do is, starting at index n equals 0, I write out first 3 terms of the series. And then when the index starts at 1, I write out the first 3 terms of the series. And they're the same series, you see. So a lot of times it's helpful, and you'll see this in, if you take differential equations from Math 282, it's helpful to change the index of a series. And remember, a convergent geometric series, if you have, there's a formula in the book, okay, that says the following. It says that, I showed this to you. Now, we didn't prove this, but if you have a series of this form, and this is the general form of a geometric series, that's going to equal A divided by 1 minus R when the absolute value of the common ratio is less than 1. So this form here is what I have here in the red box. I wanted to rewrite the series in the form given in the textbook in section 8.2. And the common ratio R we've identified as 1 over root 2. And the A has to be 1. What other number can I put there? Has to be a 1. So you see the sum is going to be then 1, which is A, divided by 1 minus the common ratio, which is 1 minus root 2. If you have 1 over 1 minus 1 over root 2, you can multiply the numerator and denominator by root 2. And that would get you then root 2 in the numerator. And of course, in the denominator, you're distributing that root 2 here and here. And so you're going to get in the denominator root 2 minus 1. And that's what we get here. Okay, and that's what WebAssign would want. It would not accept a decimal for that. for that. You know, WebAssign, well, it's simplified radical form answers. Okay, and are there any questions on that? All right, if you're good with that, let me just look at the book real quick. I want to look at example 3 with you from the textbook. Um, all right, I assume we're good then. Let me go to the textbook here because we only have about a few moments here. Book has some great examples in section 8.2. Yeah. So this problem says, is this series convergent or divergent? The series goes from n equals 1 to infinity. This is example 3 from section 8.2. N equals 1 to infinity. And the term of the series is 2 times 2 raised to the power 2n, times 3 raised to the power 1 minus n. It kind of looks like a mess, right? Well, what you have to do is you have to rewrite the series in a more pleasant way. Okay, that's what you have to do. That's what they want you to do. So look at what they do here. Let's look at the work that they got here. So they say, okay, let's take 2 to the 2nth power. So we're thinking geometric series, right? When we look at that series in example 3, we're thinking, could we express that as a geometric series? Because if we did, then we could tell based on what the common ratio is whether the series converges or diverges. Well, 2 to the 2nth power you can write as 2 squared raised to the nth power, and 3 to the 1 minus nth power is like 3 to the power negative quantity n minus 1. Well, they bring then the 3, they rewrite that series as the series where n equals 1 to infinity of 4 to the nth over 3 to the n minus 1 power, and that's just equal to the series, hold on, the series, one moment, the series where n equals 1 to infinity of 4 times 4/3 to the n minus 1. Okay, so let me just go to the whiteboard real quick and show you that last step, because I think they could have put in a few details on that. I want to just show that to you. So this is finishing up example 3 in the book here, from section 8.2. I mean, here's the series, and see what you can do is you can write this as 4 to the nth power over 3 Actually, let me do this. No, I'm going to write this. I'm sorry. Hold on. Yeah. I'm going to leave the denominator alone, and I'm going to write the numerator as 4 to the nth power, n minus 1 power times 4 to the first power. Okay, and this would allow me then to say 4 times 4/3 to the n minus first power, because you see you can take this part here and write it as 4/3 to the n minus 1 power. So 4/3 is your r and 4 is your a. And so this is a geometric series. It's a geometric series with r equals 4/3, which is greater than 1. Right, 4/3, which is greater than 1. I'm sorry, man. This big font, it gets a little bit sloppy at times. Let me just fix it here. And so this means then that series has to diverge. You see what they did here? Okay, and if we go back to the book here, now they say we recognize this series as a geometric series with a equals 4. Hold on, a equals 4 and common ratio of 4/3. And since a is greater than 1, the series diverges. How many are feeling good with this? Give me a thumbs up if you're feeling good with this. I mean, I know you need to practice, but is this how many are kind of liking this material, liking section 8.2? Okay, Gabriel's liking it. I'm glad to hear that. Do we have one more person? All right, Victoria. Thank you, Victoria. Excellent. Are there any questions before I stop the recording? Okay, I'll stop the recording then.